Molecule diffusion is noisy. A single molecule in a fluid gets bombarded with other molecules, and this results in Brownian motion. In previous videos, we've explained how the path of a diffusing molecule can be constructed with Gaussian random numbers. Let's talk about how this single molecule motion leads to counting the number of molecules seen at a receiver. This leads to a statistical description, and it's very important for understanding the communication performance in a diffusion-based system. Let's assume that we have a payload of molecules that are released at a transmitter, and we want to count the number of molecules seen at a receiver. Since diffusion forces molecules to move randomly, the molecule count will be a random number. If we know the channel impulse response of this system, then we can figure out the statistics of the received signal. By statistics, I mean that we can't predict the molecule count exactly, but we can say the chance of every possible count. Mathematically, these predictions are described as probability distributions. For the sake of example, let's take a channel impulse response that we've seen before, which is the unbounded point-to-point channel. This says how the molecule concentration varies over time and space when molecules are released at a point into a diffusion-only fluid with no chemical reactions or obstacles. If we take this response, or more generally whatever the channel is, for one single molecule and integrate it over our observation area at a given time, then this is the chance of seeing the molecule at that precise time. In the single molecule case, we only have two possibilities. We either observe the molecule or we don't. So we have an uncertain event, is the molecule observed at this moment, and the outcome of this event can be described as a Bernoulli random number based on the integrated channel impulse response. This is like flipping a coin, but the chances of heads and tails are not the same. Almost always, the chance of not seeing the molecule is higher than the chance of seeing it. With the properties of random variables, we can extend the single molecule case to multiple molecules. If we release a group of molecules at the same instant, and they don't affect each other, then the chance of any specific molecule being observed at our receiver is still the integrated channel impulse response for one molecule. However, we can now describe the total number of molecules observed. We just have to add up the individual Bernoulli random numbers, which all have the same chance of being observed, and this sum is a binomial random number. It turns out that the binomial distribution can be challenging to use, so there are two popular approximations. First, if the chance of seeing any one molecule is small, but the overall number of molecules released is high, then it's accurate to use the Poisson distribution, whose average is the multiplication of chance of seeing one molecule and the total number of molecules. Second, if the average is high enough, then we can approximate the Poisson distribution with the Gaussian distribution. But hold on, we also use the Gaussian distribution to describe the diffusion of individual molecules. Are these the same distribution? Actually, no. The Gaussian for diffusing molecules is based on the diffusion coefficient and simulation time step. The Gaussian for molecule observations is based on the diffusion coefficient, the number of molecules transmitted, and the time and location of the observation. So these two Gaussians have different parameters. The time-varying molecule distribution is an important piece of the puzzle to describe communication performance. By knowing how likely we will count a certain number of molecules, we can measure whether a particular signaling scheme can be successful and how often. We'll see examples of molecular communication schemes and their performance in future videos. Thanks for watching. Did you learn something? You can let me know in the comments. You can also like the video and subscribe if you'd like to see more research highlights and tutorials on biophysical communication engineering. See you next time.